As you may have already realized through the years of math classes and homework, math is sequential in nature, meaning that each concept is built upon prior work. Arithmetic skills are necessary to conquer algebraic concepts, which are then developed further to be used in calculus, and so on. As you're building these concepts over time, the math process may become automatic, but the reason or justification for the work may be long forgotten. In this video, we will go back to the basics to review the commutative, associative, and distributive properties of real numbers, which allow for the math mechanics of algebra and beyond. The names of the properties that we're going to be looking at are helpful in decoding their meanings. Consider the word commutative. What do you think of when you see this word? When I look at this word, I see the word commute. That word reminds me of move, which is pretty much what the commutative property allows you to do when adding or multiplying algebraic terms. The commutative property looks like this mathematically. Let's take a minute to remember the definition of an algebraic term. It is a number, variable, or product of coefficients and variables. Examples of algebraic terms are 3, 3x, 3xy, 3xy squared, and so on. To prove that moving or rearranging terms is acceptable, let's look at a few examples of the commutative property being used in addition problems. If we add 5 plus 3, we get 8. But if we switch our terms and make it 3 plus 5, we still get 8. So 5 plus 3 is equal to 3 plus 5. Let's alter one of our terms a bit for this next example. 5 plus negative 3 equals 2, and negative 3 plus 5 still equals 2. So 5 plus negative 3 equals negative 3 plus 5. Note that there is a very important distinction between the addition of a negative integer and the operation of subtraction. It is important to note this distinction because the commutative property does not apply to the operation of subtraction. For instance, 5 minus 3 does not yield the same as 3 minus 5. This property also does not apply to division. 100 divided by 2 does not equal 2 divided by 100. The commutative property does, however, apply to multiplication. For example, 4 times 3 times 5 is equal to 5 times 3 times 4. Let's do the math just to make sure. 4 times 3 is 12, times 5 is 60, and 5 times 3 is 15, times 4 is also 60. Even though we switched around the terms, we got the same result. Our final example involves the use of variables. Simply substitute values for the variables to show that rearranging terms is acceptable when adding and multiplying. Let's let x equal 1, y equal 2, and z equal 3. You could substitute with any values, but we'll use these three for now. So this gives us 3 times 1 squared plus 5 times 1 times 2 plus 3 equals 5 times 1 times 2 plus 3 times 1 squared. 3 times 1 squared is 3, plus 5 times 1 times 2 is 10, plus 3 equals 10 plus 3 plus 3, which gives you 16 equals 16. Once we add each side, we are left with 16 on both sides, which is true. 16 equals 16. The next property that we will look at is the associative property. Again, the name provides a helpful hint to its meaning. What comes to mind when you hear the word associative? For me, the word associate stands out, which could also bring to mind the word group. Accordingly, the associative property allows us to group terms that are joined together by addition or multiplication in various ways. Parentheses are used to group the terms, and they establish the order of operations. Work inside the parentheses is always done first. Mathematically, the property looks like this. Let's look at an example of this property used in an addition problem. This example will show that adding the last two terms first or adding the first two terms first simply does not matter. Let's take a look at 3 plus 4 plus 5 is equal to 3 plus 4 plus 5. So if we do what's in the parentheses first, 4 plus 5 equals 9. 3 plus 4 equals 7. And 9 plus 3 is 12. And 7 plus 5 is also 12. So 12 equals 12 because it's on both sides of the equation. Likewise, the order that we perform multiplication does not matter either. Let's say we have 3 times 4 times 5 equals 3 times 4 times 5. 3 times 4 is 12 times 5, and 3 times 4 times 5 is 20. 12 times 5 is 60, and 3 times 20 is 60. So 60 is equal to 60. The commutative property of multiplication shows that it is acceptable to rearrange terms when multiplying. In contrast, the associative property of multiplication moves parentheses to order the multiplication. And finally, the last property we'll be looking at is the distributive property, which looks like this. The notation once again dictates that this property applies only to the operations of multiplication and addition. Specifically, if a term is being multiplied by an expression in parentheses, then the multiplication is performed on each of the terms. Here is an example to prove that this algebraic move is justified. The parentheses on the left tells us first to add 3 and 7. So we have 2 times 10 is equal to 2 times 3, which is 6, plus 2 times 7, which is 14. 20 is equal to 20. The sum of the products on the right side of the equation gives the same result as multiplying on the left. Okay, now that we've gone over the 3 properties, let's test your memory. For each problem, state the property, commutative, associative, or distributive, that justifies the statement. Go ahead and pause the video if you need more time. Think you got it? Let's see. The answer for number 1 is the associative property, because the parentheses are moved to order the multiplication. The answer for number 2 is the distributive property, because 3 is multiplied by both terms in the parentheses. That leaves us with the answer to number 3 being the commutative property, because we've simply rearranged the terms. As you can see from our work in this video, you have been using the commutative, associative, and distributive properties for quite some time without even giving the why much thought. You will be asked to think about these concepts again in higher-level math courses when some of these properties simply do not hold up. Until then, keep using these rules with confidence to guide your work and thought processes.
Hey guys, welcome to this Symmetrics video on fractions. Fractions can be simple or complex. In this video, we'll cover different types of fractions and how to add fractions with different denominators. So, what is a fraction? A fraction is a part of a whole, which means a fraction can never be a whole number. Think of it like this. Our circle is divided into 8 equal pieces. Let's say 3 pieces were filled in. That means that 3/8 of our circle is filled in. The top number is called the numerator. And our bottom number is called the denominator. When saying fractions out loud, the denominator will usually be spoken as the ordinal version of the number. You would say eighth instead of 8, or third instead of 3. Let's take a look at a list of our denominators and see how we would say them. As you can see, there are a couple of exceptions. If our denominator is 2, you could say half instead of second. Or if our denominator is 4, you can say quarter instead of fourth. But either one is acceptable. Hopefully that helps you to understand how fractions are defined and also how to actually say them out loud. But there are different types of fractions. Let's take a look at those. First, we have a proper fraction. A proper fraction always has a numerator, which we looked at, that is smaller than the denominator. Our example that we used before, 3/8. So our numerator, 3, is smaller than our denominator, 8. Some other examples of proper fractions include 4/5. An improper fraction is the opposite of a proper fraction in that the numerator is larger than the denominator. So while 3/8 is a proper fraction, 8/3 is an improper fraction because the numerator is larger than our denominator. Improper fractions are always equal to or greater than 1. That means that 9/9 is an improper fraction since it's equal to 1. There are also mixed fractions, which contain a whole number and a proper fraction. Here's an example. Note that the whole number 2 is followed by the proper fraction 3/4. We also have equivalent fractions. Equivalent fractions are two different fractions that name the same number. For example, 6/8 and 3/4 look different, but they're the same. 3/4 is just a simplified or reduced version of 6/8. To simplify 6/8, you just divide the numerator and the denominator by 2 to get 3/4. Now that we know the different types of fractions, we can explore how to add them. If two fractions have the same denominator, adding is a breeze. You just add the numerators together, and that gives you the answer. For example, so notice what we did to get 3/4. All we had to do was add from our first fraction the 1 from our numerator, and from our second fraction the 2 from our numerator. Add them together to get 3, and we just bring over our 4 from the denominator. Simple. But what happens if the denominators are different? Well, in that case, you have to convert the denominators to be the same. So let's take a look at an example. You can't really simplify 3/8 into anything that would easily add with 1/2, but we can do something with 1/2 that we could easily add with 3/8, and that's multiplying 2 by 4, which would give us 8. But whatever we do to our denominator, we also have to do to our numerator. So that would look like this. So our equation now becomes 3/8 plus 4/8 equals 7/8. Subtraction works the same way. If you're subtracting fractions with the same denominator, you can just subtract the top numbers, like in this example. So in this example, all we had to do was subtract our top numerators here, which gave us 2/4, which simplifies to 1/2. Simplifying numbers just makes them easier to work with. But if you're subtracting with a different denominator, you have to make the denominators match. For example, so in this example, 3/8 minus 1/4 is equal to x. We're kind of looking at a same issue like we did over here. We need our denominators to match. So we need to find out what can we do to make our denominators match. Well, in this case, we can multiply 4 times 2. But remember, we have to do the same thing that we do to the denominator, we must do to our numerator. So we can multiply it times 2, and then here's what we get. So once we multiply our second fraction here by 2, we get 3/8 minus 2/8, which gives us 1/8. So these problems were pretty easy because they had either the same denominator or were just really easy to convert. But let's look at one more equation that's a little trickier. So at first glance, it doesn't look like these numbers have much in common such that we would be able to multiply or divide 4 by anything to get 7, or 7 by anything to get 4. So a lot of the times when you have problems like this, what you end up having to do is multiplying this fraction by the denominator of the other fraction. And likewise, we would multiply this fraction by the denominator of this fraction. So here's what that looks like. So after our multiplication, we end up getting a common denominator, which is 28. So now all we have to do is add our numerators together, which that gives us 45 over 28. And that's our answer. With this calculation, we found the least common denominator. The least common denominator is the smallest common number between denominators. Anytime you perform a calculation with different denominators, you must find the least common denominator to solve the problem.
Hi, and welcome to this video on ratios. Ratios are used all the time in many aspects of our lives. In this video, we'll review what ratios represent and how they should be interpreted. As mentioned, ratios are frequently used, but sometimes not fully understood. Simply put, ratios are an efficient way to compare numeric values of different categories. For example, let's say that you have a room of 20 people comprised of 12 women and 8 men. The two categories are men and women, so your ratios would look like this. The ratio of women to men is 12 to 8, and the ratio of men to women is 8 to 12. Note that ratios can be simplified by dividing both values by the common factor of 4, which will not change the meaning of the ratio. The simplified ratio still represents the relationship of the number of women to men, 3 to 2, and the number of men to women, 2 to 3. There are two ways that ratios can be written. This example uses a colon, but you could also use a division bar to form a fraction. 12 over 8 simplifies to 3 over 2. It is very important to note that the order of the categories matters when building a ratio. The first value is technically referred to as the antecedent, and the second value is referred to as the consequent. The antecedent is always compared to the consequent. Interpreting the ratio in context can sometimes be tricky, but becomes easier with practice. Let's look at some examples of ratios you might come across in day-to-day life. Cooking. You are making a batch of your mom's delicious salad dressing. The recipe calls for many ingredients, including 2 cups of extra virgin olive oil and 3 cloves of chopped garlic. In this case, the ratio of oil to cloves is 2 to 3, or 2 over 3, and the ratio of garlic to oil is 3 to 2, or 3 over 2. In cooking, you might hear this referred to as 2 parts oil, 3 parts garlic. This is because the units here are different, cloves versus cups. Shopping. Grocery store displays allow us to compare the value of products based on their unit cost. Many times, this is simply a quick ratio of cost to unit, with the unit being ounce, pound, etc. Suppose you're scanning the cereal aisle and narrow your choice down to your 2 favorites. You decide to be practical and base your decision purely on cost. Both have similar prices, but the volume of the packaging is different. Calculating a quick ratio of cost to unit for each box will reveal the better value. Brand A costs $5.79 and has a volume of 20.35 ounces. Dividing the price by the volume gives us the cost of the cereal per ounce, 28 cents. Brand B costs $6.39 and has a volume of 24.15 ounces. Dividing the price by the volume gives us 26 cents per ounce. Despite being a higher cost per package, choice B is a better value by unit price. This example was fairly straightforward because the volume of the cereal packages were both measured in ounces. Many times a unit conversion must be made before a unit price can be determined. For example, if we're trying to compare the unit cost of a pound of fresh broccoli to a package of frozen broccoli measured in ounces, we would need to know that 1 pound is equal to 16 ounces before we could calculate the unit cost ratio. In this case, the frozen broccoli would be the better value based on the smaller unit price per ounce. So, as you can see, ratios are common in our everyday lives, and you've probably been using them whether you have realized it or not.
Multiplying decimals may seem like a daunting challenge, but in this video, we'll show you the techniques you need to decimate this decimal dilemma. In order to understand decimals, you first have to understand place value. Every number has a value based on its place relative to the other numbers. Let's look at the number 1,762. Based on place value, the number to the far left has the largest value. In this case, the number farthest to the left is in the thousandths place. The second number farthest to the left, our 7, is in the hundredths place. The third number, 6, is in the tens place. And then our last number here, which is farthest to the right, is in the ones place. Here's another way to think through this. So what we see when we do that is we should be able to multiply whatever number is in a specific place value. We should be able to take that number and multiply it times its place value. So in this case, it's in the thousands place. So we should be able to multiply it by 1,000, multiply 7 by 100, 6 by 10, and then 2 by 1. And so again, we're multiplying every number by its place value. And then when we add it all up, we should get the total, which is equal to our number. So now any number behind our last number, so in this case 2, is called the tenths place. And this is where decimals come into play. Let's look at 1,762.8. The 0.8 behind the number 2 equals 8/10 of 1 whole. So that was a review of numbers in their place value. Let's take a look at how to actually multiply decimals. You multiply decimals just like you would normal whole numbers. The trick is understanding how and when to move the decimal point so you get the right answer. We'll use this equation to show how it's done. Remember place value. That means 45 1800ths multiplied by 0.5 or 5/10. So let's figure this out. In solving this problem, pretend just for a moment that the decimal point isn't there. That would give you this equation. You don't need the 0 since it doesn't add anything to the equation. If we solve this equation, we get, but we're not done. We have to figure out where to place the decimal. Here's how you do that. Go back to the original equation and count how many numbers are behind each decimal point. In this case, there are 3, 2 here and then 1 here. We're almost done. Now that we know there are 3 numbers behind the decimals, we go back to our answer and place the decimals 3 places from the last number. So the first number we got was 22,590. But remember, we have to move our decimal point 3 places to the left because we had 3 numbers behind our decimal point here. So when we do that, our decimal point ends up right after our 22. So our final answer is 22.59. So that's our look at multiplying decimals. As you can see, the concept seems much harder than it actually is. If you understand place value and how to move the decimals in the right place, you'll do just fine. Hey guys, welcome to this video on dividing decimals. Dividing decimals may not seem like the most useful tool, but it can actually come in handy for several situations in everyday life. Now, you may be wondering when dividing decimals would ever be useful. Well, let's say you had $26.84 in your bank account, and you wanted to buy gas for your car without going over your budget. Each gallon costs $3.69, and you'd like to tell the attendant how many gallons to put in your car. How many gallons of gas should you ask for? Or let's say you're constructing a house and you need pieces of wood that are 4.85 feet long. The local store sells large beams of wood that are 28 feet long. At the store, you wonder how many pieces of wood can you cut out of each beam. Having the ability to divide numbers with decimals would help you in these situations. Let's start with a basic example. Say you wanted to divide 4.5 by 0.5. Your first step would be to write out the problem as you would any other long division problem. It should look like this. When solving this problem, it would be significantly easier to work with whole numbers instead of numbers with decimals. The simplest way to accomplish this is by multiplying each number in the expression by 10. As a general rule, every time you multiply a number by 10, you are essentially moving the decimal point over one place to the right. If we multiply 0.5 and 0.4 by 10, we get. Now you would solve 45 divided by 5, as you normally would. Since this is a relatively straightforward problem, we don't need to go through the steps of long division. 5 times 9 is 45. You may be wondering if we need to do something to modify this answer. After all, we did change both numbers in our expression. How can the answer be correct for our original expression? However, if you pull out your calculator, you'll see that dividing 4.5 by 0.5, our original expression, also yields 9, just like dividing 45 by 5. Let's try a more complicated example. We'll divide 15.75 by 3.5. The first step is to multiply each number by 10 in order to turn these numbers with decimals into whole numbers. Starting with 3.5, that would give us 35. However, if we look at the other number in our expression, 15.75, we notice that multiplying it by 10 once does not suffice. That would give us 157.5, which is still not a whole number. So then what do we do in this instance? Remember, a key rule in dividing numbers with decimals, you need to do the same thing to both numbers in the expression. To make 15.75 a whole number, we need to multiply it by 10 twice. Or you could say we need to multiply it by 100. That in effect moves the decimal place over 2 places to the right, giving us 15.75. As we mentioned, we need to do the same thing to both numbers. So now we multiply 3.5 by 10 twice, or by 100. We move the decimal over 2 places to the right and add a 0 to the empty space. So now we have 1,575 being divided by 350. The problem is now long division. 350 does not go into 1, 15, or 157. So we need to guess how many times it goes into 1,575. 350 goes into 1,000 around 3 times. So 4 would be a good estimate for the number of times it goes into 1,575. Let's do some quick multiplication to double check. 350 times 4. So when we multiply 4 times 0, we get 0. Now we multiply 4 times 5 to get 20. So we carry the 2. 4 times 3 is 12, and then we add the 2, which gives us 14. So then we have 1400, which is the best fit we're going to get into 1575. So now we write 4 above our 5. So now we have 1400 being subtracted from 1575, which leaves us with 175 left over. So now we want to be sure to add a decimal after the 4 on the top as well. Now we divide 1750 by 350 with some trial and error. Given that we saw before that 350 times 4 was 1400, we can see that 350 times 5 is going to give us exactly 1750, which means that we add a 5 right after the decimal place right next to our 4. This gives us a final answer of 4.5. While dividing decimals may have seemed daunting at first, remember that it is essentially the same as regular long division. Don't forget the strategy we discussed in order to turn our numbers with decimals into whole numbers. Multiply both numbers in the expression by a multiple of 10 to move the decimal point over as many times as necessary. Treat both numbers the exact same way, and you'll be sure to end up with the correct answer.
Rates are spoken about and used every day in many aspects of life. The concept is pretty straightforward, as rates are nothing more than ratios of values that represent different units of measure. The values that are being compared are called the terms of the rate. Let's consider the treasure trove of rates that may be in your grocery cart the next time you go shopping. In the examples listed here, the rate that you agree to pay is simply the cost related to the quantity of the product. Let's say we have a 12-ounce box of pasta, which costs $1.49. The rate is then $1.49 per 12 ounces. If we have a pound of deli meat and the cost is $9.99, our rate would then be $9.99 per pound. Lastly, let's say we have an 8-pack of 20-ounce bottles of soda, and the cost is $5.98. Our rate then is $5.98 per pack. If we look at this last example a little closer, we'll see that there is room to break down the rate even further. The example provides the price of an 8-pack. But what if I want to determine the cost of one 20-ounce bottle? The ratio of $5.98 to 8 bottles provides that information. This quick calculation tells me that each 20-ounce bottle costs approximately 75 cents. This breakdown to determine the cost per bottle may be helpful to determine whether I buy the 8-pack of one type of soda or the individual 20-ounce bottles of another brand on sale for 50 cents each. The process of breaking down the cost to a smaller unit reveals the unit rate of the product. This is helpful to make informed decisions at the store, as the volumes of product in various packaging are often different. By comparing unit rates, savvy customers are able to make price comparisons based on common units of the product, regardless of packaging and advertised sale prices. Let's break down the soda cost per bottle further to determine the cost per ounce. If one 20-ounce bottle costs roughly 75 cents, then dividing that cost by 20 ounces reveals the cost per ounce. So 75 cents per ounce divided by 20 ounces gives you roughly 4 cents per ounce. As you can see, breaking down costs to the smallest unit reveals the cost savings of the sale. Of course, saving a few cents per ounce of soda may not be the deciding factor of your purchase. Other factors come into play when consumers are shopping, like brand loyalty and personal preference. However, comparing unit costs provides an objective way of making consumer choices based on the price. The important thing to remember when analyzing unit rates is that the units must be the same. Let's consider another example to illustrate this point. Suppose you are on a road trip in Wyoming, and on the first day you covered 300 miles in 4 hours of mostly highway driving. You can quickly determine your average rate of speed as miles per hour with the following calculation. Coincidentally, your friend is traveling in Germany, where the standard unit of measure is in kilometers, and she reports that she covered approximately 513 kilometers in 4 hours on her first day of the road trip. Her average speed would be calculated as Clearly, this is comparing apples to oranges in the sense that the underlying units are not the same. A conversion of either miles to kilometers or kilometers to miles must be made to make a fair comparison of average speed. Keep in mind that a kilometer is a shorter unit of distance than a mile. 1 mile is equal to approximately 1.609 kilometers. To convert your average speed of 75 miles per hour to kilometers, simply multiply 75 by 1.609. On the other hand, you could convert your friend's reported kilometers per hour to miles per hour. 1 kilometer is equal to approximately 0.6215 of 1 mile. Multiply this conversion factor by your friend's daily average speed to convert to miles per hour. The way that you convert does not matter as long as you compare the average speeds of the same unit. Both conversions show that your friend in Europe traveled at a faster rate on the first day of her trip.
Why do we classify numbers? Why do we give them names like integers, irrational numbers, or negative numbers? For the same reason we classify anything. We want to make sure that everyone has an understanding of what specific numbers are called and what they mean. After all, there's a difference between 25 and negative 32 and 4 to the 6th power. In this SMOmetrics video, we'll provide an overview of numbers and their classifications. Numbers are our way of keeping order. We count the amount of money we have. We measure distance. We use percentages to indicate a sale. Numbers are an integral part of our everyday existence, whether they are whole numbers, rational numbers, or the first type of numbers we're going to look at, real numbers. A real number is any value of a continuous quantity that can represent distance on a number line. Essentially, it's any number you can think of. 50 is a real number. 1 billion is a very large real number. Real numbers encompass 3 classifications of numbers, which we'll talk about in a little bit. Whole numbers, rational numbers, and irrational numbers are all real numbers. Imaginary numbers are not real numbers. They are complex numbers that are written as a real number multiplied by an imaginary unit, I. For instance, the square root of -1 calculates as the imaginary number I, and the square root of -25 is 5i. Even though imaginary numbers aren't real numbers, they do have value. Electricians use imaginary numbers when working with currents and voltage. Imaginary numbers are also used in complex calculus computations. So just because these numbers are called imaginary doesn't mean they aren't useful. Whole numbers are numbers that we count with. 1, 2, 3, 4, and 5 are all whole numbers. So are -17 and 0. Whole numbers do not have fractions or decimals. All whole numbers are called integers. Integers can be positive or negative whole numbers. All integers and whole numbers are part of a bigger group called rational numbers. This group also includes fractions and decimals. That means that 3/5 and 7.25 are rational numbers. Rational numbers can also be positive or negative. Rational numbers have opposites, which are called irrational numbers. These numbers can't be written as a simple fraction. Pi is the most famous irrational number. We have a close approximation of how to calculate pi, but it's just a close approximation. Pi is renowned for going on and on forever. That's why it's an irrational number. You can't easily write it as a fraction. Natural numbers are those that are positive integers, although there is some debate as to whether natural numbers start at 0 or 1. Negative numbers are, well, exactly that. They are the numbers below 0. There are several other number classifications as well. Numbers are divided into even and odd numbers. If you can divide a number by 2, that number is even. So 24, 36, and 74 are all even numbers because if you divide them by 2, you get 12, 18, and 37. Even numbers always end with 0, 2, 4, 6, or 8. Odd numbers can't be divided by 2 and leave a whole number. Any odd number divided by 2 will leave a fraction. So 17 divided by 2 is 8.5. 23 divided by 2 is 11.5. All odd numbers will end in 1, 3, 5, 7, or 9. Numerators and denominators form fractions, which are comprised of 2 integers. The number on top is the numerator, the number on the bottom is the denominator. The numerator, the top number, shows how many parts we have. The denominator, the bottom number, shows how many parts make a whole. Let's say you have 6 apples and 3 of the apples get eaten. The number of apples you have left over would be displayed as 3/6. You would then divide 3, the top number, into 6, the bottom number, to determine the percentage of remaining apples. In this case, the number is 50%. So that's our look at numbers and their classifications. From whole numbers to irrational numbers, we need to know what to call numbers so we can know what they mean.
Let's start by defining array. Array is a line with a single endpoint that extends infinitely in one direction. If we take this ray and add another ray to it that has the same endpoint, we've created an angle. We've also created a vertex, which is the point where 2 rays meet. You can think of it as a corner. We usually see vertices whenever lines meet or in polygons like triangles and quadrilaterals. Sometimes we have many angles, so in order to tell them apart, we have a system for naming them. Here's our simple angle again, but with a few points added on the rays. Now we can refer to our angle as angle ABC. When naming angles with 3 letters, the vertex point must be in the middle. Here, B is the vertex, so the B goes between the A and the C. We can actually call this angle CBA, and it is just as correct. If the point that is the vertex is only a part of one angle, then we can use a shorter name. In this case, we could also call this angle B. Be careful though, because sometimes a single point can be the vertex of multiple angles, like this. In this case, we'd have to call the angles by their long names, because point B is the vertex of angles ABC, DBC, and DBA. If we asked someone to just look at angle B, they wouldn't know which of these we meant. So it's important to be precise when dealing with more than one angle. Sometimes angles will be labeled with numbers inside the arc, like this. Now we have an additional name for this angle. We now call it angle 1, or we can call it angle ABC, or we can call it angle B. Since most of us have 3 names, it's only fair that angles have a bunch too. But most of the time, we like to use letters to name our angles, since the numbers could be confused with the measure of an angle. Sometimes you'll see lowercase letters instead of numbers, or Greek symbols like theta or alpha. Speaking of measuring, remember the protractor? We use it to measure angles. If we were to place one on our trusty angle, we would find that it measures 45 degrees. If we wrote this out, we would write it like this. The measure of angle ABC equals 45 degrees. The measure of an angle is important in classifying angles, as we're about to see. Let's look at a variation of our 2-ray angle, but this time let's make it so that they are perpendicular to each other, which means the angle between them is 90 degrees. Here, we've created a right angle. Notice that it has a different angle symbol than our first angle. Instead of an arc, It has a square. Whenever we see an angle with that square, we know it is exactly 90 degrees. We most often see right angles in squares, rectangles, and right triangles, but they can appear in other places too. When an angle has a measure that is smaller than 90 degrees, it's called an acute angle. Our original angle would be part of an acute triangle since it measures 45 degrees, which is less than 90. If we make an angle so that it has a measure that is greater than 90 degrees, we create an obtuse angle, which looks like this. In this case, angle ABC has a measure of 140 degrees, which is greater than 90. Obtuse angles also have to be less than 180 degrees. Those are the three main types of angles as determined by measure. But there are two more oddballs we need to know about. The first is a straight angle. It looks like a straight line and it has a measure of 180 degrees. When it's drawn like this, we can see that angle ABC does exist and has a measure of 180 degrees. This is a useful thing to know because we'll need it to understand linear pairs later on. But before we get to that, let's look at the other oddball. This one doesn't look like an angle at all, but in fact, it's called a full angle. Imagine we rotated point A counterclockwise, with point B staying where it is, until it lined up with point C again. How many degrees is that? It's all the way around the circle, which we know is 360 degrees. Remember our straight angle? What if we drew that but added another ray sticking out of it, like this? If we know that angle DBC is 55 degrees, and we know that angle ABC is a straight angle, and therefore 180 degrees, we can actually find angle ABD. How? By taking the whole straight angle, ABC, that measures 180 degrees and subtracting the smaller angle, DBC, that measures 55 degrees. 180 degrees minus 55 degrees equals 125 degrees. This is called a linear pair. Two angles, ABD and DBC, combine to form angle ABC, which is a line. And because the two smaller angles add up to 180 degrees, we can also say that they are supplementary angles. Something very similar happens with right angles. Here's our right angle from before, but with another ray in the middle. Angle DEF is a right angle. We can see that angle DEG and angle GEF together completely fill angle DEF, which means they add up to 90 degrees. So if we know one of the two angles, we can find the other one by subtracting its measure from 90 degrees. For instance, if angle DEG is 30 degrees, then we know that angle GEF is 60 degrees, because 90 degrees minus 30 degrees equals 60 degrees. Angles that add up to 90 degrees are called complementary angles. Let's go back to our obtuse angle one more time. There's one more type of angle that's been hiding in plain sight that we need to be aware of. We can see that angle ABC is an obtuse angle, which means it's more than 90 degrees and less than 180 degrees. But what about the other side? This is called a reflex angle. It's always more than 180 degrees and less than 360 degrees. Every acute, right, and obtuse angle has a reflex angle. Next, let's take a look at where we'll see some of these angles in the wild, or at least in geometry problems. Let's start by looking at two lines that intersect. In this case, we've numbered the angles. Whenever we see a figure like this, if we know any of the angles, we can determine all of the others. So if angle 1 measures 130 degrees, we can figure out angle 2, because those two angles together form a line and are a linear pair and supplementary. So angle 2 must be 50 degrees. The same works for angles 1 and 3. And then we can use what we know about angle 2 to pair it up with angle 4 to find that angle. When it's all said and done, it looks like this. Notice that the angles opposite one another have the same measure. These angles are called vertical angles, and they're always congruent, which is geometry speak for having the same measure. Now, let's look at three lines intersecting. This is called a transversal. Once again, we've numbered the angles and there are red arrow marks on two of the lines, indicating that they are parallel. A transversal doesn't have to have parallel lines, but when it is, it allows us to know a lot about the 8 angles created by the intersecting lines. But before we get to that, let's look at the 8 angles. We can see they are in two groups of 4, angles 1 through 4 and angles 5 through 8. Angle 1 is in the top left position in the top group of angles. If we look at the same spot in the bottom group of angles, we see that angle 5 is in the top left spot for that group. That means that angles 1 and 5 are corresponding angles. So angles 2 and 6 are also corresponding angles because they're in the top right spot for their respective groups. Angles 3 and 7 are also corresponding, as are angles 4 and 8. In a transversal, when there's a pair of parallel lines, corresponding angles are congruent. When the lines are not parallel, the corresponding angles are not congruent. In the case of our diagram that does have parallel lines, if we know that angle 2 is 55 degrees, we then know that angle 6 is also 55 degrees. And once we know that, we can use what we learned about vertical angles and linear pairs to find all the others. That's all we need to know to find our angles, but there is some more location-based vocabulary we need to be aware of with these types of problems. Interior angles are the angles between the parallel lines. In this case, that's angles 3, 4, 5, and 6. The exterior angles are the ones that, you guessed it, are not between the parallel lines. So angles 1, 2, 7, and 8 are exterior angles. Alternate angles are angles that are on opposite sides of the line that cuts across the parallel lines. And same-side angles are angles that are on the same side of that line, of course. In questions about the two groups of angles, this is used to combine interior or exterior with alternate or same-side angles. The question will always relate to the other group of angles. Something like, what is the alternate interior angle for angle 3? We would look to the other group of angles, then to the other side of the intersecting line, and then find the only angle that is an interior angle, which would be angle 6. The same side interior angle for angle 3 is angle 5. That's a lot to absorb in a small amount of time. Try these questions to see if it's sunk in. What is the alternate exterior angle to angle 8? The answer is angle 1. What is the same side exterior angle to angle 7? The answer is angle 1. What is the corresponding angle to angle 5? The answer is angle 1.
Hi, and welcome to this review of different types of triangles. Before we begin, here's a review of the basics. A triangle has 3 straight sides that connect. The length of the sides can vary, but the length of the largest side can't be equal or greater to the sum of the other 2 sides. In addition, a triangle has 3 interior angles, and the sum of these 3 angles are always 180 degrees. This is true for all triangles, including the 6 types we're looking at today. We're going to break our 6 types of triangles into 2 groups of 3. Let's start with the 3 types of triangles that are categorized by the measure of their largest angle. These are the acute, right, and obtuse triangles. But how do you know which is which? Take a look at the largest angle of each triangle and note whether or not the angle is more than, less than, or equal to 90 degrees. We can see that the largest angle in the triangle on the left is 70 degrees. 70 is less than 90, so this is an acute triangle. Just remember that acute angles are less than 90 degrees. This one is easy to remember, since cute things are often small, like puppies and kittens. We can see that in the middle triangle, the largest angle is exactly 90 degrees. You might remember that a 90-degree angle is a right angle, so this triangle is a right triangle. Finally, in the triangle on the right, the largest angle is 117 degrees. Because this is more than 90 degrees, this is an obtuse angle, so we call this triangle an obtuse triangle. That's all there is to it for these 3 types. We just find the largest angle, and the name of the triangle will correspond to the name of that angle. Our second set of triangles is categorized by how many of the sides have the same length. Here are 3 triangles with the lengths of the sides included. In the triangle on the left, we can see that all 3 sides are the same length and measure, 9 centimeters. A triangle like this one where all the sides are the same is called an equilateral triangle. It's not too tough to remember the name since the beginning of equilateral sounds like the word equal, and the word lateral means side. In the middle triangle, we can see that 2 of the sides are the same length and measure, 8 centimeters, while the third is 9 centimeters. When 2 of the sides of a triangle are the same, it's called an isosceles triangle. It's a hard one to spell, but an easy one to recognize. In our last triangle, none of the sides have the same length, so this is called a scalene triangle. While you often see these 3 types of triangles identified by the lengths of their sides, they can also be categorized by their angles. It works exactly the same way. When all the angles are the same, 60 degrees, it's called an equilateral triangle. Technically, it's called an equiangular triangle, but they're exactly the same thing because all equilateral triangles are also equiangular triangles. When two of the angles are the same, it's an isosceles triangle. And when none of the angles are the same, it's a scalene triangle. So far, we've covered 6 types of triangles, which is technically all of the types, but we're not done yet. If we wanted to be really specific when naming our triangles, we can combine names from each group, one from the first group and one from the second group. For instance, this triangle is an acute scalene triangle. Its largest angle is less than 90 degrees, so it's acute, and none of its angles are the same, so it's scalene. Before we go, how about you give it a try? Pause the video and identify these 2 triangles by choosing either acute, right, or obtuse, and then choosing equilateral, isosceles, or scalene. Think you got it? The triangle on the left is an obtuse scalene triangle, while the one on the right is a right isosceles triangle.
Hi, and welcome to this video on diagonals. Today we're going to explore the diagonals of parallelograms, rectangles, rhombi, and squares, and see how these shapes relate to each other overall. All of the shapes that we're going to look at today are quadrilaterals, meaning they are all 4-sided polygons. A polygon is a shape with multiple sides. A parallelogram is a quadrilateral that has 2 sets of parallel sides. The blue arrows denote which sides are parallel to each other. The opposite sides of a parallelogram, marked by green tick marks, are congruent, which means they have the same measure. A rectangle is a shape we all know well since it appears in the real world so often. But one thing we don't usually think about is that rectangles are just a special kind of parallelogram. That means that the opposite sides are both parallel and congruent, just like our first parallelogram. What makes a rectangle a special parallelogram is that its interior angles are all the same. In fact, they are all right angles, which means they measure 90 degrees. Another special parallelogram is a rhombus. It has all the properties of the parallelogram, but all of the sides of a rhombus are congruent. Note that the tick marks are all the same, which tells us that all the sides are the same length. Our last special parallelogram is a rectangle and a rhombus at the same time, so it has the right angles of the rectangle and the congruent sides of the rhombus. It's another shape we all know well, the square. As you can see, the opposite sides are parallel. All the angles are right angles, and all the sides are congruent. So let's recap quadrilaterals before we start exploring their diagonals. Here, we've arranged our quadrilaterals into a sort of tree, starting with the square as the trunk. Every square is a rhombus, and every rhombus is a parallelogram. Every square is also a rectangle, and every rectangle is a parallelogram. That's how it works going up the tree, but it doesn't work going down. Not every parallelogram is a rectangle, and not every rhombus is a square. Okay, let's explore the diagonals of these 4 quadrilaterals. A diagonal is a line segment connecting opposite vertices, or corners, of a quadrilateral. Here's our regular, non-special parallelogram with the diagonals shown. As you can see, the diagonals of a parallelogram bisect each other. In other words, they cut each other in half. We could add some numbers to illustrate this better. Or we could use tick marks to show that the diagonals have been bisected. Since the 3 special quadrilaterals we're talking about are all parallelograms, they will have bisecting diagonals. Now, let's look at the rectangle. Here's a rectangle with its diagonals. The diagonals of a rectangle are congruent, and again, since a rectangle is a parallelogram, the diagonals bisect each other, making each half the same length. Each diagonal of a rectangle also divides the rectangle into 2 congruent right triangles. This means that, if we wanted to, we could calculate the length of the diagonal using the Pythagorean theorem. Now that we've got rectangles figured out, let's see what happens with another special parallelogram, the rhombus. Once again, since every rhombus is a parallelogram, the diagonals bisect each other. The diagonals are not the same size though, so what's special about this one? Take a look at the angles at which the diagonals intersect. These angles look like they could all be the same, and since there are 4 angles there, it must mean that each angle is 90 degrees. This means that the diagonals of a rhombus are perpendicular to each other in addition to bisecting each other. Okay, only one quadrilateral left, the square. Remember, the square is a parallelogram, a rectangle, and a rhombus, so it should have all the properties of those shapes. 1, the diagonals will bisect each other. 2, the diagonals will be the same length. And 3, the diagonals will be perpendicular to each other. Let's see if we're right. We were right. If we look closely, we can also see that the two diagonals cut the square into 4 congruent isosceles right triangles. Now that we've looked at our 4 parallelograms and their diagonals, let's finish with a review to see what all you can remember. Which of the following statements is false? A, every rectangle is a parallelogram. B, every rhombus is a square. C, every square is a rectangle. D, the diagonals of a parallelogram bisect each other. E, the diagonals of a rhombus intersect at right angles. F, a diagonal of a rectangle divides it into 2 congruent right triangles. G, the diagonals of a rectangle are the same length. H, a quadrilateral whose diagonals bisect each other, intersect at right angles, and are congruent must be a square. The correct answer is B. Remember the tree? Not every rhombus is a square, but every square is a rhombus.
Let's start off by defining volume. Volume is the measurement of how much space a liquid or gas takes up, or how much space a liquid or gas takes up within a given object. You may not know it, but people use volume every day. Volume is used to calculate drinking amounts. The amount of water you can hold in a cup is dependent on the volume of the cup. There are several other ways that volume is used. Now, let's take a look at how to calculate the volume of a triangular prism, a rectangular prism, a sphere, and a cone. The volume of a triangular prism. The area of a triangle is area equals 1/2 base times height. Essentially, to find the volume of the triangular prism, you're multiplying the area of the triangle times the length or the depth. So the formula for the volume of a triangular prism would be volume equals 1/2 base times height times length. Let's take a look. We have a triangular prism with a height of 8 meters, a base of 13 meters, and a length of 4 meters. All we have to do is plug our numbers into our formula, then solve. So we have volume equals 1/2 times base times height times length. And once we solve, we get our answer, which is 208 meters cubed. It's important to know that when dealing with volume, we'll always have cubic units because we're multiplying the units by themselves 3 times. Volume of a cube or rectangular prism. To find the same volume of a cube or rectangular prism, you will use the same formula. Just like with the triangular prism, you want to find the area of one side, then multiply it times the length. However, it's important to know that the formula you use to find the area of a triangle is not the same formula used to find the area of a square or a rectangle. The formula for the area of both a square and a rectangle is area equals base times height. So, to find the volume of a cube or rectangular prism, you would find the area of the square or the rectangle, then multiply it times its length, which makes the formula volume equals base times height times length. Here's an example. Here we have a cube, which is a rectangular prism, but all the sides are perfect squares. Because it's a cube, we know that all of the sides are the same distance. So all we need to do is multiply 10 times itself 3 times. This gives us 1,000 meters cubed. Let's try another. Here we have a rectangular prism with sides that are different in distance. We have a base of 12 centimeters, a height of 8 centimeters, and a length of 6 centimeters. Now all we need to do is plug those numbers into our formula, and once we solve, we get 576 centimeters cubed. Volume of a sphere. Now if you remember, the area of a circle is A equals pi times r squared. That is pi times the radius squared. Well, to find the volume of a sphere, you will use a similar formula, but multiply it times 4/3 and switching the r squared to make it r cubed, making the formula for the volume of a sphere V equals 4/3 times pi times r cubed. Now, you can do what is called a proof to prove that this is the formula, but for now, we'll just go ahead and plug the numbers into the given formula. The sphere has the diameter of 20 meters. This is all the information we need to plug in and solve for our equation. We're looking for the radius, and we know that the radius is equal to half the diameter, which means that our radius is equal to 10 meters. When we plug 10 into our formula and solve, we get 4,188.9 meters cubed. Volume of a cone. The formula for volume of a cone is very similar to the formula for the area of a circle. However, there are two things added to the formula. To find the volume of a cone, you multiply times 1/3 and times the height, because now you have a height because you're working with a three-dimensional shape. This makes the formula for the volume of a cone, volume equals 1/3 times height times pi times r squared. Here's an example. Here we can see that we have a height of 5 centimeters and a radius of 2 centimeters. Once we plug in all of our numbers, we have volume equals 1/3 times 5 centimeters times pi times 2 squared. When solved, we have volume equals 20.94 centimeters cubed. Great job, you guys. Learning new formulas can be hard. The important thing is to keep practicing so that you're able to recognize which formula you need to use and to memorize the formulas. I hope this was helpful. Be sure to check out more of our videos by subscribing below. See you next time.